Now. Okay. Welcome again, everyone. Thank you so much for being here today. Thank you for being so patient with all of these scheduling emails and for all the polls that we sent. We're really excited to share all the modeling results that we've come up with and really dive into how we can apply them for our adaptation planning in Los Angeles County. To get started today, we'll be doing some introductions, and to start us off, I'll pass it off to Phyllis Griffman.
Hi, everybody. Good morning. Thank you so much for being here and taking time out of your day. I know how busy everybody is. I'm Phyllis Griffman. I'm the Executive Director of the Sea Grant program at USC, and along with Karina, the Director of our Adapt LA project. For those of you who don't know what Sea Grant is a NOAA state university partnership. We fund relevant research for this region, and our program in particular is based on helping to solve the problems of the urban ocean. What happens when you put 18 million or so people right next to a very fragile coast and becoming an even more fragile coastline as we go forward. And the other piece of our Sea Grant mission is to make sure that the results of funded research get to the people who need them, to the decision makers and the public and policymakers. Adapt LA was basically started around 2011 when we first had initial COSMOS, coastal ocean storms modeling results. And I see Patrick Barnard here in the crowd. And we started working with the city of LA and then regionally with the coastal cities in LA along Santa Monica Bight to do vulnerability assessments and then begin to help people understand their adaptation options. So to understand methodologies and options for responding to the vulnerability assessments. Next slide, Karina, please. So I'll just acknowledge that University of Southern California and the lands on which we work on the Southern California Bight is located on the unceded, sacred, and traditional lands of the Tonga, Achamen, and Chumash nations, the first native peoples. They are the original stewards of this land. They continue in this role today. Thanks, Karina. And with that, I will hand it back to Karina. And Kevin and Michelle for what I think you'll find very interesting results of the environmental effects of sea level rise project modeling.
Thank you, Phyllis. So Phyllis gave us a bit of an introduction into Sea Grant and our Adapt LA project, but we also want to take time to connect with each other. Some of you already know each other, but we want to allow enough time for this kind of collaboration and networking as much as we can in this virtual space. I want to just give us an idea of what today's going to look like. I shared the agenda with you all, but I just have a summary here, and I'll include the link in the chat as well, in case you'd like to reference it throughout the day. After our introductions, we'll have the presentations and demonstrations of the tool that we've developed. Then we'll have a breakout session to discuss everything that we've seen and develop kind of a list of what we want and need in order to make this as applicable as possible. Then we'll have some extra time for discussion and Q&A. We've really allotted a lot of time for that to make sure that we can dive into this as much as necessary or as much as we want to. And then we'll have a closing. We may have, depending how long we need for the discussion and Q&A, we may have a bit of extra time that you get back to your day. But again, we wanted to just make sure that we had a lot of time for that. So now that we all kind of know each other a bit better, I'll just give an overview of the project a bit. So I sent these links in the emails that we sent, but just in case you're looking for them now, I've sent over the project website on NOAA's page and then the story map summarizing our previous efforts on this project. So This project, which is a part of the Effects of Sea Level Rise program within NOAA, focuses on sea level rise, groundwater, and adaptation. Like Alderon mentioned, we have the portion in the Santa Monica Bay that we're looking at, and then we have a portion in Humboldt Bay that our partners, that Michelle and Kevin are also working on, but they're working with partners up there for those workshops. So we can see what groundwater and adaptation, sea level rise look like in an urban setting and in a rural setting. And as part of that, we're looking at both natural and nature-based features and conventional infrastructure for controlling coastal flood hazards. And again, the goal of all of this is that we inform decision makers like you all with the most effective uses of these strategies to protect the coastline. So we want to get out of today. You saw this on the agenda that we sent over, but just to kind of center us again, overall, our goal is to learn what you need for applying this information and data. What that'll look like is we want to present the results that we have so far, as well as the online data viewer that we mentioned. And we'll be looking a lot at Marina Del Rey today because that's where we've developed most of the results and the data platform for. But it's kind of a model for what might be helpful or what might work for other places. And so, although we'll be focusing a lot on this area, we want you to think about what is applicable to your region as far as the modeling frameworks and the criteria that we've evaluated go. We want to create a kind of wish list of what you'd like to see in both the modeling and in this presentation of data. And then we want to identify the benefits and limitations of what we have so far. And lastly, we want to just facilitate discussions between you all and the researchers, but also with each other on how we can apply this to our adaptation planning. And just a bit of a recap of the project timeline overall. So as you saw in the story map that I linked in the chat, we started with virtual workshops in fall 2020 to inform the project design. So that's where we identified which focus areas within the Santa Monica Bay we really wanted to hone in on in high resolution. And then now we're in summer 2023 where we're disseminating the results that we have so far. Since the fall of last year and going into the fall of this year, we're conducting these one-on-one workshops with each of the focus areas, so Malibu, Marina Del Rey, and South Bay, to look at the results so far and really engage with those community members, interested parties, to make sure that that the results that we're coming up with, that the models are helpful. And then after that, in late fall, or after these one-on-one virtual workshops, we do want to have in-person site visits and workshops with each of these focus areas. And so we'll coordinate with you all as that gets closer, but just to have on your radar as we move forward in the year. Okay. So that wraps up kind of the intro. Without further ado, I'll pass it off to Kevin and Michelle to start sharing the results.
Thank you, Karina. Let me share my screen. Okay, are you able to see the full screen?
Yes, looks perfect.
All right, great. Thank you again, everyone, for being here. We're excited to share some of the results from our project with you all. So I know that most or a few of the folks on the call today have been part of previous workshops for this project, but I do want to provide a brief overview and refresher on our project goals and approach for those who may not be familiar. It sounds like we have some new faces as well. So as has been mentioned, our project is funded by NOAA through the Effects of Sea Level Rise program, and we aim to develop modeling tools that can be used to evaluate the costs, benefits, and trade-offs between different shoreline adaptation strategies that are aiming to mitigate impacts from sea level rise and storms, both to surface water and to groundwater systems. So these modeling tools allow us to consider surface water flooding driven by tides, waves, and surge, as well as the groundwater dynamics that may create additional hazards in coastal communities. So for our analysis, we're focusing on coastal California, looking at study sites in Santa Monica Bay and in Humboldt Bay. And we hope that by working within these two systems and comparing results between them, we can address local needs and priorities that are specific to each region, while also identifying common solutions that can be applied more broadly across coastal systems. So our model framework that we're applying uses Cosmos, the coastal storm modeling system that Patrick and his team developed to simulate coastal hydrodynamics. And this allows us to model waves, storm surge, tides, overland flow, and river discharge. And then from those Cosmos outputs, we can then extract
Oops.
I'm sorry.
That's okay.
Okay, can you hear me okay?
We can
now?
hear you, but we can't see your slides. There we go. Perfect.
Okay, did I cut out at all or you were okay?
You aren't cutting out.
Okay. Let me, I'm sorry, I don't know what is going on here, but so from this Cosmos model that allows us to look at surface water impacts, we then extract water levels along the coastline, which are used as input to a groundwater flow model built using ModFlow. And so ModFlow then simulates how the water table responds to changes in coastal water levels and allows us to map areas with shallow or emergent groundwater tables that could potentially result in flooding. So within both of these models, we can then implement various shoreline adaptation strategies to test how they affect both the surface and subsurface water levels and the potential for flooding. So we're evaluating a number of different adaptation strategies that span this green to gray spectrum. So some of those strategies include natural or nature-based approaches on the green side of the scale, like marshes or dune restoration, as well as engineered approaches like seawalls and tide gates. And for each of these adaptation strategies, we can simulate those within our coupled modeling framework and then calculate a range of impact metrics that allow for comparison between the effectiveness and risk reduction potential of each of the strategies. So some of the metrics that we're looking at include flood area and flood volume, which are taken directly from Cosmos and ModFlow. Model outputs from these models are then used in combination with building stock data and depth damage curves from FEMA's HAZIS program to estimate economic damages to structures, including both residential and non-residential structures within the study area. And that data is also then combined with population data from the Census Bureau to estimate the population displaced due to flooding and their demographic characteristics. And in particular, we can look at total population characteristics as well as having a focus on groups that are typically considered vulnerable based on social vulnerability theory. So through a series of previous workshops, which some of you folks have attended, we identified 5 primary priority sites for flood hazard assessment and outlined a range of possible gray and green shoreline adaptation approaches to test. We ultimately selected 3 of those areas for more in-depth modeling and analysis because they were most reflective of the different types of conditions that we can see within Santa Monica Bay. So these include Marina del Rey and Venice, where we are modeling seawall, dune, and tide gate scenarios, as well as Topanga Lagoon and Beach and Manhattan and Hermosa beaches, where we are modeling seawall, dune, and beach nourishment strategies. And today, as Karina mentioned, we want to focus on the results specifically from Venice and Marina del Rey to illustrate the types of insights that our modeling framework can provide, and to also get everyone thinking about what information might be most relevant for you and might be most helpful to inform your planning in the region. So you can see here the study area for the Marina del Rey and Venice study site. The surface water model, again, built using Cosmos, includes coverage of the entire Santa Monica Bay, which you can see in the panel on the left. And then it also includes a series of higher resolution grids covering Marina del Rey and Venice that provide us with more detailed information about the flow and flood dynamics within that area. The full model coverage is outlined here in this dashed line, but our impacts analysis, which I will be presenting shortly, focuses primarily on areas north of Ballona Creek. So within this model, we tested a set of 9 adaptation scenarios, as well as a no action scenario that leveraged the current shoreline configuration. 3 of the scenarios that we considered are dune scenarios or nature-based type approaches along Venice Beach. The first of these, shown on the left, is a targeted dune scenario. And so here we assumed that permanent dunes are implemented at the locations where the LA County Department of Beaches and Harbors typically constructs winter berms to reduce wave impacts. So at the moment, those are temporary, only constructed each winter, but we were testing if these were made permanent, how much protection would they provide? The second scenario implements dunes at the lowest elevations along the beach in all areas with elevation less than 4 meters, reference to NAVD 88. And then the final scenario on the right implements dunes in all areas with elevation less than 5 meters, NAVD 88, which ends up being the entire beachfront. And then for each of these 3 scenarios, the actual dimensions of the dune, so the height and width of the dune, are similar to the dimensions of the winter berms that are implemented by the Department of Beaches and Harbors. In addition to these more nature-based approaches, we also evaluated 2 engineered strategies, including building a seawall along Venice Beach and constructing a tide gate across the mouth of the harbor in Marina del Rey. And in addition to these 5 individual scenarios, so we have 3 dune scenarios and 2 engineered strategies, we also looked at combinations where we coupled the dune and seawall scenarios with the tide gate alternative so that we would have protection along the beach and at the mouth of the harbor. We modeled each of these scenarios in Cosmos, assuming a 2-meter sea level rise scenario, since this is the point at which widespread flood impacts start to occur within this area. And so this can be viewed as kind of a long time horizon planning exercise. But we could also look at additional sea level rise scenarios in the future as well. And then finally, we simulated both an average tidal condition, or what we call the no storm scenario, along with 3 storm scenarios, a 1-year storm, a 20-year storm, and a 100-year storm, consistent with the approach that Cosmos takes. Okay, so let's take a look at some of the results and the questions that can be addressed using our findings. So an obvious first question that we might have here is, which of these strategies are most effective at reducing flood impacts within the region? And our approach here allows us to answer this question across multiple criteria, including hydrodynamic, economic, and population metrics. So you can see in this slide, the flood area, building damages, and displaced population impacts summarized here for the whole study area. And in this case, the black bars that you see in these charts represent the impacts that would occur if no adaptation was implemented. The red bars here represent the engineered strategies, including the seawall, the tide gate, and the combination of those 2. The blue bars represent the nature-based dune strategies along Venice Beach. And then the orange bars represent hybrid strategies that combine the dunes with the tide gate at the harbor. So we see here that the strategies targeted along the beach, including here this seawall strategy shown by the first red bar and the dune strategies shown by these blue bars, These strategies provide between 40 and 60% reduction in flooded area for our storm scenarios. So from our 1 year to the 100-year storm, these are providing about a 50% reduction in flooded area, and similarly, about the same amount of reduction in exposed population. However, when we look at building damages, if we again look at this first red bar and these 3 blue bars, we see that these beach-focused strategies are less effective and provide a maximum reduction of only 20% in building damages for the 100-year storm. And this is due to the fact that the highest building damages are typically centered around the harbor, where flood depths are higher. And you can see that here in this top map, which shows the flood depth resulting from the 5-meter dune scenario. So although this provides substantial protection along the beach here and in Venice, we see that there is still significant flooding around the marina. Now, if we look at the tide gate strategy in the harbor, which is represented by this second red bar here in the plots, we see that this tide gate scenario provides the largest reduction in building damages. So here in this bottom plot, we see very large reductions in building damages as a result of the tide gate construction across all storm scenarios. And in addition, it also provides the largest reduction in flooded area and exposed population for all storms except the 100-year storm. So it also is providing substantial benefits from a flood depth and area perspective, as well as an exposed population perspective. Strategies that include protection along the beach and at the harbor entrance, like the one you see down in this bottom panel with the 5-meter dune and the tide gate. These can provide complete reduction in flooding and impacts across all criteria. So it appears from this assessment that having a tide gate or some kind of barrier at the harbor entrance would provide substantial benefits for the area across all of the criteria that we considered. However, our modeling framework allows us to dive a little deeper into this and further examine this finding while considering more granular impacts between different neighborhoods and also across vulnerable populations. So let's first consider how the impacts vary between neighborhoods. And in particular, we analyzed the results for the areas surrounding the Venice canals separately from the rest of the domain. And as a result of this, we noted important contrasts between the effectiveness of these different strategies. So for example, although the tide gate provides flood reduction benefits across all scenarios, as we just discussed, when we look at the entire domain, it's far less effective in the Venice canals. As we would imagine, the tide gate is providing protection to the harbor, but not really providing protection along the beachfront. So we see here this red bar in the plots represents the tide gate scenario. It provides minimal reduction in flooded area across the no storm, 1-year storm, and 20-year storm conditions. And it actually increases flooding here. So we see that the red bar is higher than the no action black bar here. It increases flooded area by 20% under the 100-year storm scenario. And this occurs because when we construct the tide gate, it blocks flow into the harbor and redirects floodwaters toward the beach, which leads to a more extensive amount of flooding. The negative effect of this tide gate is also notable when comparing the targeted dune scenario shown here in blue with the targeted dune plus sluice scenario shown in the orange bar. And so we see that for this 100-year storm event, the addition of the tide gate actually increases flooded area by more than 150% compared to constructing the targeted dunes alone. And we can see that here in the maps as well. When we just have the targeted dunes in place, flooding is eliminated, or sorry, when the targeted dunes are in place here, we see that there is some amount of flooding in the Venice canals area. But when the tide gate is added, even though it reduces flooding substantially around the harbor, we can see that it increases flooding in the Venice canals. Other strategies here that provide protection along Venice Beach and either in combination or not with the tide gate, they are very effective at reducing flooding in the Venice canals across all of the storm intensities that we considered. So this really suggests the importance of providing beachfront protection in addition to protection at the harbor for this particular region. And overall, this finding highlights the importance of quantifying variations in flood impacts across the communities or neighborhoods within the study region for each of our adaptation strategies, because if we look at impacts at an aggregate scale across the entire area, we may overlook some of these disparate effects on certain neighborhoods, like what we're seeing here for the Venice canals. And so this suggests that, you know, if it is decided that some kind of tide gate or barrier would be constructed across the harbor, that care needs to be taken, that significant protection is also provided along the beach to prevent shifts in flood risk from the harbor area to the Venice Beach and Venice Canals region. And then finally, we can also consider these potential disparate impacts on vulnerable groups within the study area. And so the graphs that you're seeing here show differential impacts between the percent of child, senior, minority, or low income populations that are exposed to flooding as compared to the percent of the total population exposed to flooding. So as an example of this, if we look at the child population graph here for the 100-year storm, the tide gate strategy is shown by this negative red bar. And we see that this provides 14% less benefit to children as compared to the total population. And this is because children comprise a lower percentage of the population in census blocks that surround the marina, which is protected by the tide gate, versus the census blocks along the beach that are not protected by the tide gate. However, we see that this is actually in contrast to the impacts for minority and low income populations. So when we look at the minority and low income populations, the tide gate actually provides slightly higher benefits to those populations compared to the total population, whereas other strategies that are focused on the beach, like the seawall and the dune scenarios, provide relatively smaller or less protection for those populations compared to the entire population. And this type of information can be critical for stakeholders by providing them with a more comprehensive view of the potential benefits and trade-offs between these adaptation strategies. And I think it's especially critical in efforts to develop more equitable solutions that address coastal hazards and coastal flooding, because it allows us to identify potential disproportionate impacts to certain vulnerable populations in the planning phase as we're doing this modeling work, so that these effects can be properly addressed and mitigated before project implementation. So I want to also mention here that this analysis has been published as an open access article in the Frontiers in Marine Science Journal, and it can be accessed at the link here on the slide, which we'll also share in the chat. So please feel free to review this after the workshop if you'd like to explore the findings in more detail. And if you have any follow-up questions on this as you're reading, please feel free to reach out to us. So at this point, I'm going to turn it over to Kevin, who will talk a bit more about the groundwater focus of the project.
All right, thanks, Michelle. So Michelle's already given you plenty to think about, I'm sure, and we will have an opportunity with the web viewer to dive more into those data. That will be what we're going to be exploring here in just a little bit. But part of this project is to understand how all these surface water changes are connected to groundwater, and on timescales that are potentially more relevant than what the original Cosmos data groundwater side worked with. And so we only use the long-term average groundwater changes with the Cosmos groundwater data sets that we put out and that are on our CoStar Future and the Hera web viewer. And so with this project, it gave us the opportunity to look at, well, how does a storm impact water table elevations, and how does that affect saltwater intrusion potentially? And then what can we do about it? And so we are very focused on these adaptation strategies in this spectrum from green to gray infrastructure. And I think something from Michelle's presentation that really struck me when I've seen this work a ton of times, that it is so important to work across regions and across different communities. And so that's why we all have you kind of at this workshop together, so that we can start these conversations and think about how your jurisdictions might overlap and connect to other jurisdictions, and how the decisions matter at the base scale. And so with these various adaptation strategies, we do want to think about how groundwater will be affected. And so if you go to the next slide, Michelle, we'll see that there are chances that they'll change groundwater flow. And so they could change groundwater levels and saltwater intrusion. And so the work that I've been doing on this project, if you go to the next slide, has been trying to understand how these various especially gray adaptation strategies, more of our traditional adaptation choices, could affect groundwater flow and could affect both saltwater intrusion and flooding. And so this work is in review right now at a journal article at Water Resources Research. But what you can see on the 2 rows are 2 different styles of what we can do to block saltwater intrusion. And so the top one is a cutoff wall. This is more like a seawall with a deep foundation. And this has been proposed as a way to reduce saltwater intrusion. The subsurface dam on the lower row is actually more effective. You'll see that it blocks more of the red, salty groundwater from intruding. But the problem is cutoff wall is easier to construct, more likely to already exist with a lot of the seawalls or different bulkheads that are developed. And what happens, what we found with this research, is that it acts as a dam to groundwater. And so you'll see that little white arrow is representing groundwater flow. Towards that vertical white line is that barrier that's gray in the picture on the left. And so we actually see that groundwater discharges inland of the barrier. And this is bad news because this is going to raise water tables inland of the barrier. It could cause groundwater flooding inland of seawalls if there isn't sufficient drainage or pumping that happens inland of it. And then if we have pumping inland of our barrier meant to keep out intrusion, we could have more intrusion because of that. And so there's a cascade of effects. If intrusion is the original concern that you want to create various infrastructure for, then you could have the groundwater flooding as an outcome of that. Or if you were trying to just block surface water flooding and you create a seawall that has too deep of a foundation, this could also cause some groundwater emergence problems and require massive amounts of pumping. And so this is still a developing kind of piece of research, but I wanted to show you some of these early results. You go on to the next slide. We are actually coupling Michelle's model outputs to a full-fledged groundwater flow model. And so the pretty colors here in this slide are showing mostly the outputs of Michelle's model that are going to control where the groundwater table is right at the edge, right along the coastline. The red areas that are actually there are the places where the groundwater table is at the land surface. And so areas where we have groundwater flooding or groundwater emergence. And we're running this for a variety, all of the different versions of adaptation strategies that Michelle used, we're running for groundwater. But then we're also saying, well, what if we add some sort of dam or barrier in the subsurface that will then deflect groundwater flow even more? And so it spirals off into hundreds of different scenarios that we haven't really figured out how to write. And as clean of a kind of output that Michelle shared and that we'll be looking in this viewer. But these are the types of questions that we're asking and where we're going with this work with groundwater. And so I know a lot of people, when you were doing your introductions, were saying that you're interested in the groundwater side of this. And so from preliminary results from the Marina del Rey and Venice areas, you'll see that there are not many little red dots in these simulations, and that as we have a storm coming in, the simulation in the animation is only a few days long. And so this is the Cosmos storm that comes in and how water tables respond over the course of just a couple of days. That the good news is that water tables aren't responding very drastically to this short-lived storm surge, but the effect of different types of infrastructure do have a huge effect. And so on the left-hand side here, you'll see a line of red that kind of follows along the coast. That's an area of groundwater emergence, because hidden right inside of that, that's right following along of the 4-meter dunes that Michelle was talking about, but I've actually installed a cutoff wall in the model that's below those dunes. So more of a hybrid type of adaptation strategy, a green and gray. And you'll see that it causes groundwater emergence right on the inside of those dunes. And so the adaptation strategies connected with long-term sea level rise are the primary drivers that we're seeing for groundwater emergence, and that the storms are relatively small. It will depend on various geological properties and also how long lasting the storm is. But we're seeing that mostly the groundwater is responding over longer timescales and to major infrastructure changes. All right, and with that, I'm going to pass it back to Michelle to introduce the web tool, and then we will get to start talking.
All right, thank you, Kevin. Okay, so we're excited to be able to share this web tool with you. So I want to spend a few minutes demoing this web tool and data viewer. It was developed by the NOAA program management team here, led by Christine, to support the sharing of model results from this project. So we have a link here on the slide, and that will also be in the chat as well. But before you dive into looking at this on your own, I want to provide here just a quick overview and explain how you can use this and walk through an exercise where we might ask a particular question and be able to use this tool to answer that question. So before we do a live demo, I just want to provide here a quick overview. So we have the tool here has two parts. The top section that you will see when you access the link allows you to view flood depth maps for each of the adaptation scenarios that we've modeled, and to view side-by-side comparisons between two scenarios. So here on the side panels of each of these maps, you can select which adaptation scenario you want to look at. The flood map here will update based on that scenario, and you can select two different adaptation strategies on either side to do a direct side-by-side comparison. For example, here I'm showing the no action scenario on the left, and you can see the flood depth that results from that scenario. And then we can see on the right what happens if we create these targeted dunes. How is flood depth and flood patterns affected as a result? And then secondly, the bottom section of the tool provides graphical summaries of economic damages and impacted populations across 4 storm frequencies that were considered in our modeling. So for the economic impacts, which are here on the top row, you can view total economic damages specifically to residential structures, as well as benefit cost ratios calculated using the total economic damages and estimated construction costs for each of the scenarios. And then in the bottom row here for population impacts, you can view the total impacted population, as well as impacts for certain vulnerable groups. So here we have the low income population that's impacted, as well as the minority population impacted. And so let me switch over now to the viewer itself so that I can do a quick demo here. And then we'll work through a quick exercise on how to answer a specific question that you might have. Okay, so on the dashboard here, when you first click on the link, this should be your default view. As I said up here, we can select different strategies to do comparisons. So on the side panels here, we have the 10 different adaptation strategies, including the no action strategy. If you want to view one of these layers, you can see that the no action strategy as a default is shown in the maps. So the eye here is open. If we want to hide this layer, we can just click on that and you'll see a dash through there, and it will remove the flood depth from the map. And so for this case, I'm going to leave the no action scenario highlighted here on the left, and I will just select here. I'll turn off the no action scenario over here on the right just by clicking this eyeball, and then I will bring the targeted dunes onto the screen here, again, by pressing that eyeball button. Okay, so we have the two maps here. You can see that here for the targeted dunes, we also have a little animation showing where the strategy has been implemented within the model domain. So we can zoom in and out here, either using the scroll bar on your mouse or using the zoom in function here. And you'll notice that when you zoom in on one side of this comparison plot, the other plot will also zoom in so that we can have a consistent view of the flood depth and the domain for comparison. So we could zoom in quite a bit here if we wanted to look at the Venice canals and compare the amount of flooding that we see for the no action scenario versus the targeted dunes. Over here at the left, you can see the water depth legend. If you click on this, this will provide more context in terms of how deep the water actually is that we're showing in the maps. And there are a few other features here at the top that I just want to point out. So we have adaptation strategy descriptions. If you click on this, a little side panel will pull up, and this will just provide a description of each of the adaptation strategies that we tested for this modeling exercise. So we have dunes here. The 3 dune scenarios are described. We have the sluice, or what I've been calling the tide gate, for the marina. And then we also have a seawall. So if you want to refresh yourselves on what these scenarios were, that information is provided. And then if you click this find out more, this will actually take you directly to the journal article that I mentioned. So you can also use that link to access and read this open access article. All right, and then scrolling down here to the impact area, we can look at, again, economic damages and population impacts. So here on the left, we have all of the adaptation strategies listed. As a default, this all actions option is selected. And so each of these graphs is showing the resulting impacts across our storm frequencies for all of the adaptation options. Now you might want to just select a particular set of options to compare. So let's say I wanted to compare the same 2 scenarios, the no action scenario and the targeted dune scenario. If I click on those, only those 2 options will appear in the graphs. And now I can view the impacts across all of our storm events and all of our criteria just for those 2 scenarios. If you want to view one of these graphs in a larger format, there's also this button here in the top right. If you hover over that and click, it will expand the graph to the full scale here. All right, and then finally, we also have the links to the project webpage and the story map that Karina shared earlier, in case you'd like to access those here. And we also have our contact information at the bottom. Okay, so before we have some time for everyone to explore this, I just want to walk through a quick exercise here with an example question that we might be able to answer from this viewer. So let's say that we were interested in understanding how does dune extent influence the number of low-income residents affected by large storm flooding. So this could be a management question that we're interested in answering, in understanding how our adaptation strategies would influence low-income residents. And so I highlighted some of the key terms here in this question. So first of all, we're focusing on dune extent. So we want to look at a comparison between the dune strategies that were considered in this project. We are also focusing on low-income residents as a particular group within the larger population. And then finally, we're focusing on large storm flooding. So in this case, we'll be looking at the results for a 100-year storm event, the largest event that we considered in our modeling. So I'm going to just refresh this page here so we can start from the default and quickly walk through how we might address this question. So first of all, we might first want to look at visually how do these scenarios compare? And so again, we're interested in the dune scenarios. So I'm going to turn off the no action scenario and turn on the targeted dunes. So now we see where the targeted dunes are in place and the associated flooding. Over here, again, I'll turn off the no action scenario and turn on the dunes at 4 meter elevation. And so again, we can see the extent of those dunes and the resulting flooding. And so just by visually comparing here, we can see the largest effects are in this region here, where we do have a reduction in flooding around the canals. Now, we can only compare 2 scenarios at a time here. We can't compare 3. So I'm just going to turn off the targeted dunes and turn on the 5 meter dunes. So we can compare this 3rd scenario. And we see that with this 5 meter dune scenario, because this is providing protection along the entire beachfront, we have a reduction and almost a complete reduction in flooding on the landward side of the dunes here located along the beach. And so we can get a first estimate of how these scenarios compare just by looking at the flood maps. But what we're really interested in is impact specifically to the low income population. And so here we can go down to the impacts assessment. Again, I'm going to select the 3 dune scenarios that we're comparing: the targeted dunes, the 4 dunes at 4 meter elevation and dunes at 5 meter elevation. And I'm also going to add the no action scenario here, just so we can see how much of a reduction in flooding each of these and a reduction in impacts each of these scenarios has. So again, we're interested in low income populations. So this is the graph of interest here. I'm just going to expand that here. And then we also said large storm flooding. So we're particularly interested in the 100-year storm. And so if you hover over these points for the 100-year storm, you can see that the number of people who are considered low income and who are impacted by flooding is shown here in this pop out. So we see that for the no action scenario, there's 513 people impacted. As we move to the targeted dunes, 403 people are impacted. For the dunes at 4 meter elevation, we have 316. And then for dunes at 5 meter elevation, we have 268. And so we can extract directly the amount of people who would be impacted. And so I've summarized that here in this table. Again, this is our graph from the dashboard. This is the data that we could extract. And so we can then look at what is the percent decrease in people impacted based or when compared to the no action scenario. And we see that the targeted dunes provide some protection, about 20% decrease, whereas the dunes at 5 meter elevation provide almost a 50% decrease in impacted population as a result. So this allows for a quantitative comparison of how these scenarios are performing for a specific vulnerable group that we might be interested in analyzing. So the dashboard, I think, is really great because we have this qualitative ability to compare flood maps directly, as well as this ability to quantitatively extract values that can be used to support planning. Okay, so with that, I will turn it back over to Karina. I think we have time for questions now, and then I think we'll have more time for everyone to explore this dashboard as we move into the breakout groups as well.
Sorry, Karina.
Yeah.
I was just going to thank everybody again for being here. And those of you who are still here, thank you for hanging in with us. And your input is invaluable to this project and to the way that we go forward in helping to plan future coastal scenarios for California. So thank you all so much for taking your time and making your comments and being engaged.